I don't really see it.
Well, let's see if they're here on Zoom. Josh is on here now.
I'm here.
Hi. There we go.
Yeah. Cowboys. That's pretty bad. Dude, Donald was a beast. Watch the Seattle game? No, I was in Poland. They're good. Jamal Adams really makes their defense. I don't know, man. Like, they gave us a lot of yards to that run. But the thing was, like, they were playing really well and getting a what they're doing. I'm impressed. The Patriots with Cam Newton look pretty good. And Cam did not look good at all. Bruce Arians literally operating the class after that loss. Well, he didn't play good, so I guess he has the right to do that.
Yeah, I'm wondering why there's only just two of you.
Yeah.
Joshua has a reason, but Kinsey, Harrison, Pamela, I don't know where these guys are at. It is what it is. Also, running plays are only as good as the offensive line is helping out. If the offensive line doesn't really do a super good job, then the running plays kind of suck.
What team sports are all about.
Yeah, I mean, it helps. You can be a really good runner. But if the offensive line isn't doing its job, then it's not going to work out. So 3.3 is about the unit circle. I'm going to prove some cool stuff here. So you may know by now that this is pi over 6, pi over 4, pi over 3, pi over 2. Also, you may know what is the sine and cosine at this point. At pi over 6, what's the sine and cosine?
3 over 2.
Yeah. Yeah. What about at pi over 4?
Both 3 over 2 over 2. And then flip
Flip these, yep.
Yeah.
Over here it's 0 and 1. But why? Not only why, but how? How is this true? Well, I'll prove it to you. Remember, off of any angle, you can project a straight line and create a right triangle. That's why we care about that's why we use triangles to study circles in trigonometry. So let's construct this triangle. This is pi over 6 right here. Well, what we want to know is what is x and what is y. Okay. Well, we know that the hypotenuse has value 1 because it's just the radius of the circle, right? So you realize that this is really 30 degrees, right? So you have a 30, 60, 90 triangle, right? So this is how we kind of prove this. Assume we have a triangle, just like this one. It's 30, 60, 90. And let's say that one of the legs is root 3. One of the legs is equivalent to the value 1, and the other leg is equal to the value 2. Why am I saying that? Because this is a triangle that is possible, because 2 squared does indeed equal root 3 cosine squared plus 1 squared. Notice that this is 4 is equal to 3 plus 1. So it is indeed a valid triangle. Because if it satisfies the Pythagorean theorem, it's a valid triangle. Okay. So this, what we've invented, is a valid triangle. But here's the argument. If c squared is equal to a squared plus b squared, notice that I can multiply both sides of this equation by a half. I can scale the whole thing. Really what that does to the triangle is it shrinks it. It shrinks everything, makes the triangle half as large. So this ends up becoming c squared over 2 is equal to a squared over 2 plus b squared over 2. Notice that that gives us this triangle. This becomes a 1, this becomes a 1/2, this becomes a root 3 over 2. And it again still satisfies the Pythagorean theorem, because notice that 1 squared is equal to a half squared plus root 3 over 2 squared. That's 1 over 4 plus 3 over 4, which is 4 over 4, which is 1, which equals 1 squared. That's where everybody is. Everybody's just kind of running late. So actually, this is why. This is why cosine is root 3 over 2 and sine is 1/2. It's the argument that we're showing. Because we constructed this argument for something that has radius 2. If this is like part of a circle here, we would have constructed it for a radius 2 circle. But a radius 1 circle is the unit circle that we're talking about. So we shrink it to 1, and thus the square root of 3 and 1 turn into root 3 over 2 and 1/2. That's the cool thing about the Pythagorean theorem. You can scale it by anything and it still holds. So why is this true? This root 2 over 2 root 2 over 2 thing. That one's actually much easier to explain. And just so you know, via this, we've explained this one. We've also explained this one. That's because when you take sine of 30, you get 1/2 over 1, which is 1/2, right? But if you take sine of 60, you get root 3 over 2 over 1, which is root 3 over 2. So it depends on your reference. This is when our reference is 60 degrees. This is when our reference is 30 degrees. So I've actually proven why these two have the values that they do. All that remains to show is to prove why does pi over 4 have the values it has. Argument is quite simple. Okay, XY. So would you guys throw tomatoes at me if I were to claim that if we're at 45 degrees, that this value and that value are the same? You would agree? Yeah, because look, when we're less than 45 degrees, this value is much shorter than this long value, versus this long value is much longer than this short value. But at that special halfway point, the x and the y projections of the triangle, they're the same. So what we can set up is, I can say x squared plus y squared is equal to 1 squared by the Pythagorean theorem, but x is equal to y. So this becomes x squared plus x squared is equal to 1, which is equal to 2x squared, which I can solve for x. I divide both sides by half. Take the square root. I get the square root of 1/2, which the square root distributes. I get 1 over root 2, which when you rationalize the denominator is root 2 over 2. And that equals x, which equals y. So they're both root 2 over 2. So that's why I have those values. Here's your proof. It's really cool. I actually don't ever memorize. If I ever forget this knowledge, I can rederive it. But if someone were to memorize it and they forget it, it's done. It's over. If you get knocked in the head and you forget it, well, then it's gone. That knowledge is gone to humanity. But if you had understood it, you could rederive it and rediscover that knowledge. Okay, let's see here. Is that all this section really is? Okay, use special triangle and symmetry to locate points on a circle. Okay. To me, the most important thing about this section is, do you understand the unit circle? So there's levels to understanding the unit circle. It's not just knowing at these angles, sine and cosine are these values, but I believe as a mathematician, these derivations are the most important because they show you why those values are at those values. Why do we care? Well, this is a unit circle. All we got to do if we want to describe a point over here is expand our circle to make it of radius this, and then we can expand our circle, and we can do trigonometry still. Another right triangle at some arbitrary theta. Meaning, if we define the mathematics for the unit length, we then know everything because we can just scale it to whatever we like. If it's greater than 1, well, we multiply the whole situation by a constant that will scale it up. If it is less than 1, well, we'll multiply the Pythagorean theorem by some scalar, like a number that is less than 1, which will cause a contraction. I mean, that's really all that there is to this section. So now I have two options. I can either move on to 3.4, or I can hand out your tests and see if you guys want to talk about it. Everyone did pretty well, which makes me think I made the test too easy. All of the tests that I created, even from my other classes, people did pretty well. So I'm pretty sure I'm making the test too easy. So I might have to up it up a notch a little bit, turn it up a notch for the other tests. So don't get used to this. Okay. I also uploaded the key. Did you guys notice that? Uploaded the key. I can hand these out. If you guys have any questions about it, let me know. We could talk about any of the problems. There you go. There you go. Yeah, everybody did pretty well. You guys will be getting a lot of graded work back soon. Because I'm creating solutions and my grader will be able to hand you that information. I'd like to give you some time to look over that. You can keep it. Look over your exam. Let me know if you have any questions about it. And we could solve the problems even though the key is uploaded already on Canvas. Let me know if there's any of these problems you guys want to solve. Or if you are wondering about it. Some of them are kind of made open-ended and kind of graded really leniently. So I tend to be a lenient grader. But not this lenient, man. Yes, ma'am.
Can you go over the first part of number 11?
Sure, absolutely. I would love to. Okay, let's see. First part of number 11? You mean that negative 1,000? So let's find the reference angles for negative 1,000. A reference angle is an angle theta that lies between 90 and 0. And it's the angle, this angle must be the angle between the terminal leg and the x-axis. So I won't even like try to imagine what this negative 1,000 degrees looks like in terms of like how many rotations. It's at least 3 rotations, probably definitely more in the opposite direction. I don't even attempt to like figure out what that looks like yet. What I'm going to do is I'm going to try and get it to be a positive number because notice the definition of reference angle states that theta must be positive. So I'll add some 360s to it. How many 360s would I like to add to it? Yeah, 2 would still end up with a negative number. Yeah, 3. 3 360s. Adding it to that, I get an 80 degrees. Okay. What happens when you add 360 to an angle? It just it lands in the same spot. So it's really at the same location. Negative 1,000 and positive 80 land in the same spot. So we're talking about the same thing. There's nothing different about where it's at. Then we notice that that's that. And it's automatically, by definition, the reference angle for negative 1,000. Because it's the smaller angle in between the two angles that the terminal leg makes with the x-axis. Notice that for any terminal leg, like so, you have 2 angles here. You have a theta here, theta 1, and you have a theta 2, right? No matter how you draw it, let's say we draw it down here. Well, you'd have a theta 1 and you have a theta 2. You can always make 2 angles in reference to the x-axis, no matter how you draw your terminal leg. But the reference angle definition says pick the smaller one. So we would pick theta 1 here, and we'd pick theta 1 here. So theta 1 is like 80, whereas theta 2 would be what? 100. Want to do another one? Like 222. 222 degrees. All right, I don't know where that's at exactly. I know it goes 90, 180. It's got to stop somewhere here, right? Because this is a 270. So this is some 222. So what is this angle right here? The way you think about it is, if this is a 90, 180, 270 for the full all the way over here, Then subtracting it by 222 gives me just this angle right here. This whole rotation minus this rotation would give me that angle right there. Or actually, no, it wouldn't. No, it would not, actually. That would have given us this angle right here. What I just said would have given us this angle right here. That's not the angle we're looking for. We're looking for this angle. So a better way to teach it, a better way to explain it is subtract, every time you subtract a 90, it takes it into its analogous position in the next quadrant. So it's in quadrant 3. If I subtract the 90, it's here. Then if I subtract another 90, it would be here. Then whatever that angle it's at, it's the smallest positive theta you make with the x-axis. So how many 90s did I subtract? 1, 2, so that's 180. 270 minus 180 is
90.
oh, did I say 270?
Yeah,
Why am I subtracting it from 270? I'm
222.
so stupid sleepy right now. Oh my goodness.
It's 42.
Yeah, sleep is important, students. Don't forget to sleep. What did you? Yeah, 42. There you go. So if you're given an angle, like right here, 222 is this whole thing. I just want this little piece. So I know if I take it back 90 and 90, then it would be right here, and this angle that it's talking about is at 42, which is the same angle as right here, because of alternate interior angles. You guys remember alternate interior angles?
Yeah.
Yeah. These angles are equivalent because they're alternate interior angles. That's how I think about it. And there's the last problem. What is the reference angle for this guy? We gotta subtract a few 360s. How many? I found 4 360s to be helpful. This ends up becoming 63.69 degrees whenever you do that. And that's automatically your reference angle. Then there was the problem on the unit circle, which we talked about in class. I had to bring it up because the unit circle, in my opinion, is probably the most essential aspect of trigonometry. For them to have not included that in chapter 1, at least, I don't understand this book, but maybe the book takes a more historical approach. Any questions?
How would you do the bonus problem?
Pardon me? Oh, how do you do the bonus problem? Good question. I believe this was one of your homeworks. I think this was on your homework. One of the homework problems. I may be wrong. Here's B, here's A. I teach several classes, so. You then assign this to be a theta. You then realize, hey, what if I draw a straight line and create a right triangle? The problem begs me to do so because it says the area of the parallelogram, the whole thing, is equal to AB sine theta. So recall, this whole thing is A. And let's call this some altitude H. Okay? Notice that when I do trigonometry on this, I get sine of theta is the same thing as opposite over hypotenuse, right? So I multiply both sides by b. This implies that H is equal to b sine of theta. Then there's this really cool trick you can do with parallelograms. Let's delete this piece. This is where math is really cool to me. These proofs and the way we argue these proofs. Let's delete that piece there. Why are we deleting it? Well, it's to see something. Here's our H. This is no longer A anymore. This was A, but this piece is no longer A. Okay. Notice that this from here to here and from here to here is the same length. So this is B right here, right? It's a parallelogram. So the length here is the same as this length here. So I reproduced it. And this height here, H, is the same as this height here. So I reproduced it. Now let's add that deleted piece right here. It slides in nicely right here. Does it not? Just kind of use your imagination. This deleted piece, if I cut it out and put it right here, we get this. Notice that maybe the area of a parallelogram is a hard equation to figure out, but what is the area of this rectangle? What's the area of a rectangle? Length times what? So in this situation, it's what? Yeah, H times A. Easy as that. Then you realize that I used trigonometry over here and I figured out what H was. So if I replace H with what I solved for in that box over there, you get this. A is equal to B sine theta times A. And this clearly equals AB sine theta. Because the last time I checked, 2 times 3 times 4 is the same thing as 4 times 3 times 2. Right? So the order of multiplication doesn't matter. Proved. You're done. This is what I was hoping you guys would see and realize. This is the part of math that I enjoy. It's this stuff in math at a higher level that I really enjoy, but this is really cool. Even at this lower level, I still find it neat. Growing up, I wanted to be a cage fighter. My mom wouldn't let me. So I gotta get excitement out of life somehow. And doing these math proofs are definitely very exciting. Almost as exciting as, trying to dodge a flurry of attacks. Any other questions?
Can you do number 4?
Absolutely. Absolutely. Oh, of course. Guys, I absolutely, from the bottom of my heart, love to teach and I love to help you guys learn. So, what do they say at Chick-fil-A? My pleasure. I will show you how to do this problem. It's my pleasure. Y'all notice they say that a lot? Have you guys noticed that they say that a lot?
Yep, that's what they're saying.
My pleasure. It's kind of funny to me. I asked them one time, are y'all forced to say that? And they said, yes, they forced us to say it.
If you say it first, you might get free nuggets.
Really?
Yeah, it happened to me once.
You have to say,
My pleasure first.
I would like to order this as like my pleasure.
Yeah.
And they'll give you free nuggets.
Yep. You try it.
I'm going to, man.
Good.
That's a good pre-workout to eat like a bunch of that stuff. Gives you a lot of calories, man. I usually, when I go to Chick-fil-A, I usually spend around $80 to $100. I eat a lot of food. Not kidding. Tangent of theta over cosecant of theta minus sine of theta over cosine of theta. Let's prove that this equals sine of theta minus 1 all over cotangent theta. So let's start with this side of the equation and not assume that it equals that because we're trying to show that. Tangent theta over cosecant theta minus sine of theta over cosine of theta. Okay. Notice that cosecant is the same thing as what? One over sine of theta. Very good. Oh yeah, and I just, by the way, I switched tangent to sine over cosine because that's what you do. Everything needs to be expressed in terms of sine and cosine. That's just what you do when you prove stuff. Because sine and cosine are the fundamental trigonometric identities. Everything else is defined in terms of sine and cosine. Everything. So then I multiply by reciprocals here. So I get sine of theta over 1 multiplied times sine of theta over cosine of theta minus sine of theta over cosine of theta. Okay. Moving the calculation upwards, I get sine squared theta over cosine of theta minus sine theta over cosine of theta. Notice that I can then factor out a sine from upstairs and rewrite everything under the same denominator, cosine of theta, sine of theta times sine of theta minus 1. Notice that bringing the calculation over here, that is the same thing as tangent of theta times the quantity sine of theta minus 1. Oh, but how do we get that that's all over cotangent? Oh, that's pretty intuitive. So this is what happens when you multiply by reciprocals, right? So take that, I get sine of theta minus 1 all over. Notice that this is what happens when you multiply by reciprocals. So unreciprocate, this was like really cosine of theta over sine of theta. That we multiplied by reciprocals to get this. Does that make sense? Or should I talk more about that? If it doesn't, that's okay.
I approached the problem differently.
That's okay. So over here, look, sine of theta minus 1 is the same thing as sine of theta minus 1 all over 1. And cosine of theta over sine of theta would then be this. Notice if I multiply by reciprocals, cancel, and that would restore our original sine theta times sine theta minus 1 all over cosine of theta. So this is what we had earlier. But you just realize that tangent of theta times the quantity sine theta minus 1 is the same thing as this. And then you're done because cosine theta over sine theta is cotangent theta. So it was at this step that we were done. The rest is me just showing the details. By definition, cotangent theta is cosine over sine. And it's okay if you approach the problem differently. There's nothing wrong with that. Can't give up, you gotta keep trying. Any other questions? Would you like me to do the rest of these proofs? Okay. The explanations, I've uploaded the key. Do you guys know how to get on files on Canvas?
Yeah, like the module?
Yeah, like the module. I upload files for this class, so I've been uploading solutions to the homeworks that you guys have already turned in. So I'm working on that right now. But I already uploaded the key for this exam, so you can look at that as well for more. But you know, looking at a derivation, a piece of paper you can't ask a piece of paper questions, right? But you can't ask me questions like, wait, how did you do that? Why is that so? So it is totally worth talking about this. What does it say? Cosecant theta minus cotangent theta times cosecant theta plus cotangent theta. Everything divided by tangent theta. Let's prove that this equals cotangent of theta. So we FOIL, if you will, to get cosecant squared theta plus cosecant theta cotangent theta minus cosecant theta cotangent theta minus cotangent squared theta all over tangent theta. Okay. Then we notice that the middle terms cancel because they're the same thing, just opposite sign. So we get, this is cosecant squared theta minus cotangent squared theta. Everything over tangent theta. Then we realize this consequence of the Pythagorean identity, that, oh yeah, cotangent of theta plus 1, and this was squared, is equal to cosecant squared theta. Do I need to prove this? No, it's a Pythagorean identity. It can be proved. So then I replace that with this. The cosecant gets replaced with this. So I get cotangent squared theta plus 1 minus a cotangent squared theta, all the tangent theta. These are the same thing. Oh, well, I should be. I should say cotangent, not cosine. I just replaced this here with this here because of this relation. So then I can cancel out this cotangent squared theta. So then bringing the calculation up here, I get 1 over tangent theta, which 1 over tangent theta is defined to be what? Yep, so we're done. That's all of them, right? What is it, number 6 left? Let's prove this last one. Oh, my gosh. Ah. Ah. So let's factor out a sine from the top and a cosine from the bottom. How do I think to do that? I just see that this has a sine, that has a sine, this has a cosine, that has a cosine. Let's pull it out. Maybe something will happen. Oh, and indeed something does happen because, oh, this is the same thing as that. I just have sine over cosine, which is tangent. Sine over cosine is equal to tangent. Did you guys hear about the NASA discovery of the presence of phosphine on Venus? It means we might have just discovered a clue that there exist microorganisms on a different planet than Earth. That doesn't, we haven't verified it yet. This just came out this morning. We've not verified the microbes. We'd have to go to Venus, get a sample, and look at it to find the microbes. But phosphine is a byproduct of biochemical reactions of certain microbes in hypoxic environments on Earth. And so if they're creating phosphine as a metabolite, there could be microbes on Venus creating phosphine as a metabolite. Meaning there could be aliens on Venus. No, that is not, that's a big jump. Even the fact that there could be microorganisms there is quite a big jump because you have to verify it. You have to prove it. But if there is aliens on Venus, I want to challenge them to a math contest. Any other questions? Okay, so 3.3 is the unit circle. We derived those values, so I have no idea what else we could talk about. All the homework, just test your knowledge about the unit circle. So like certain questions, like what is a sine of negative 5 pi over 4? That's a good one. What's the sine of negative 5 pi over 4? Tell me without a calculator. Those negative angles are weird.
Is it root 2 or 2?
I don't know. I really don't know. To be honest with you, I don't know what sine of negative 5 pi over 4 is. His face, he's just like, what? What I do know, is how to derive the unit circle for any arbitrary angle, special angle, not arbitrary. We'll get to that. That requires calculus, but we won't get to that in here. I encourage all of you guys to take calculus. You what?
I have to take calculus like 3 semesters of it.
Good. I might be your teacher. Yep. Okay. So what is negative 5 pi over 4 really? I don't really understand the negative angles very well. But I understand positive angles pretty well. So why not add the 360 analog of 2 pi to see where it really is? But 2 pi is all over 1, and we need to establish a common denominator, right? So I'll multiply top and bottom here by fancy number 1, 4 over 4, so that they can have a common denominator. So this becomes a, yeah. So then what's 8 minus 5? It's a 3. So negative 5 pi over 4 is the same thing as 3 pi over 4. But 3 pi over 4 is the same thing as 3 times pi over 4. Is it not? Whoa, dude. That also means that it's the same thing as a pi over 4. Plus another pi over 4. Plus another pi over 4. Far out, dude. Right? I mean, where am I wrong? No, it does.
Oh.
So
Technically, it would be 3 pi over 4, just like that.
yeah,
Okay.
3 pi over 4 is the same thing as pi over 4 plus pi over 4 plus pi over 4. So I frame it like that because this is a pi over 4. It's a 45 degrees. So what if I added another pi over 4? Where would I get to? Over here, pi over 2. What if I added another pi over 4? This is my 3 pi over 4. So, right? You guys disagree or agree with this way of thinking? Okay, so all this question is asking me is what is the sine of theta over here?
2 over 2.
Yes, because the cosine is a negative root 2 over 2, and the sine is a positive root 2 over 2 because the y values are above the x-axis, the horizontal. So you are correct. I don't know how the heck you know this stuff so fast. I have to construct a unit circle, figure out what this angle is in positive values, then break it down to these components, and then all while not touching my calculator, figure out this equals that. I don't know how you do it, man.
Memorization.
Oh, that's not good.
Our teachers ingrained in our brains, we had to memorize the circle.
Yes,
It's crazy.
it's bad.
Really?
Yes, that's very bad
How so?
because you don't understand it. You think you do because you're coming up with the answers, but you don't really understand it. This is understanding it. Being able to relocate it using fundamental principles. I will throw you into a question, possibly on the next test. Throw you into a question that will really require understanding. A question that memorization will not be able to give you the answer. There's no way a memorization could get you there. And then you will realize, oh, now I see why that's happening. Does that make sense? So memorization is not what should be encouraged in mathematics at all. But it is. Because educators, I don't know why, either they don't understand it well themselves, they just memorized it themselves, or what. But educators don't. I went up through the public schooling system here in Oklahoma. My teachers would say the same thing, memorize it. But when you get to higher level mathematics, everything is about understanding. So memorization is just primitive. It's primitive. That's as lightly as I can put it. We are going to get more sophisticated and understand that these connections are there. Because having this level of sophistication and thought will allow you to solve much more difficult problems. And it will allow you to solve much more intricate situations because you'll understand the big picture versus just memorizing. Trust me, this is much better. It's a lot better for your brain because it works on your reasoning skills. Okay. I used to be a pre-med, and pre-meds, you have to memorize a lot of information because you're trying to go be a doctor. And you have to memorize all kinds of diseases, all kinds of bones, all kinds of nerves, all kinds of arteries. But they get to math and they think, oh, I got to memorize it all here too. But it's just not like that. Mathematics is a different subject. It's more about understanding. A good analogy is like sailing across the Atlantic Ocean. You really can't memorize how to do that. You know those boats with the wind sails? Those people weren't memorizing anything. They were like using deductive reasoning and like stars to try and like figure out, are we still north? Are we still south? Are we still east? Are we still west? Okay, let's see right here. What about tangent of negative 10 pi over 3? What is this equal to? If you've memorized it, go ahead and say it. We'll see if your memorization can match derivation. Derivation versus memorization. Derivation will always win. Any guesses? Which you guys haven't memorized this one? You can sit there and memorize all day, or you could just be lazy and learn how to think. If you learn how to think, you don't have to memorize much. All you have to memorize is a few details, and then you can just use your brain and reason your way through everything. And it's more accurate than memorization. So I'm teaching you guys how to be lazy. Isn't that what you want? I want to be lazy. So let's make it a positive angle again, because negative angles are counterintuitive. They're rotating the other way, and we're not used to that. So let's make this a positive value. So then I have to establish a common denominator, multiply top and bottom by fancy number 1, which is 3 over 3. To get that. Now what? Oh my gosh. It's still negative. Do we just give up? No, I can just add another pi over 2 pi. I'll play this game again. Negative 4 pi plus 6 pi all over 3. Because I'm multiplying top and bottom here by 3 over 3, establishing a common denominator. Now I get 2 pi over 3. All right, memorization crew. Now what? Now memorization hopefully is not kicking in. But what's the tangent of 2 pi over 3 then? Because this is the same thing as the tangent of 2 pi over 3.
If it's 2 pi over 3, it's going to be in the second quadrant.
Yes.
And then it's going to be at 120 degrees, which is negative 1/2 and root 3 over 2. And then you just have to, it's sine over cosine, so then you root 3 over 2 over negative 1/2.
Very good.
And then you get
Very good.
negative root 3.
So yeah, this ends up equaling your sine value, which is your 3 over 2, divided by your cosine value, which is a negative 1/2, multiplied by reciprocals, you get this, and these cancel, I get a negative square root of 3. This is what tangent of negative 10 pi over 3 is. What I would have done is rederive the unit circle for myself before a slew of these kinds of problems, and then realize, oh yeah, that 30, 60, 90 is really just pi over 6, pi over 12, pi over 12, pi over 6 trend. So at pi over 2, if I add a pi over 6, I would get that 2 pi over 3. Wouldn't have to memorize a thing at all. The only thing I have to do is recognize a pattern. Pattern recognition. That's what math is all about. Pattern recognition and deductive reasoning. You guys have been trained and lulled into thinking that memorization will do it all, but sadly it won't. And that's actually a good thing. It's a good thing that memorization won't do all of it. Because you know how long it takes to memorize stuff? Even if you have a really good memory, it takes a while, right? Even if you have a good memory, it takes a while to memorize stuff. But if you learn how to think about things, you don't need to memorize at all. It's less time consuming and your answers will be actually more accurate. And there's nothing wrong with the fact that you guys are trained the way you are. No, wait. There's a lot of things wrong with the way that you're trained. But it's not your fault that you were trained like that. Do not think that I blame you guys for what's happened to you. I don't blame any of you guys. I don't blame any of you guys. I blame the system, man. I blame the educational system. Okay. Moving on. I'm gonna let's see how much more can we beat this dead horse. I don't really think I want to do any more of it. Yeah, I'll move on to 3.4. Or what I could do is give you a quiz, because I didn't give you a quiz last Thursday. You guys want a quiz? Y'all really? Huh?
But if we have to take one again.
I guess, yeah. What I'll do is I'll drop probably the lowest, like, few quizzes. I'm not going to say 5 quizzes. I'm not going to say 2 quizzes. I'm not going to say 1 quiz. But I'll drop a few of them at the end of the semester, just in case someone was, like, absent and they missed it or stuff like that. So. Find the cosecant of negative 3,000 pi. Try using memorization on this one. This is, see, yeah. I was once like you guys. I remember thinking that that's how it was. And then they gave us problems like this, and I was like, wait a second. My tricks don't work anymore. Cosecant of negative 3,000 pi. I'll draw it out better. Oh yeah, and Joshua, you can email me your quiz. Let me write it out more. Negative 3,000 pi. And I will say that you don't even need a calculator for this one. But if you guys need calculators, let me know. Maybe I can go find some. Does everybody have a calculator?
Yeah.
Okay. Does anybody need a calculator? Okay. That's problem one. Here's the second problem. It's going to take a while to write. So. Second problem is a ninja, it's really Chuck Norris, performs a 360 roundhouse kick at an angular velocity of 100 radians per second. That's a pretty fast kick. You don't want to get hit with that. What is the linear speed of their kick? And I'll give some equations for you to solve. Angular speed is theta over t. Linear speed, v, is your s over t, where s is equal to r theta. You guys must be as sleepy as I am. My professor was talking about Chuck Norris doing roundhouse kicks in class. I was laughing. Any questions, Joshua? Good. Can you read the here? There you go. Now you can see all of it, right? Brilliant. Okay. Got about a few more minutes remaining, like a minute or two. All right, let's turn them in. All right, Joshua, I'm expecting an email from you soon. Thank you. Thank you. There's a stapler right here. You can staple your work.
Oh, no, these are all different ones.
All different ones. Gotcha. Okay. Yes, ma'am. Okay. Are these all different ones?
Yeah.
Okay.
Can we go over these like next class?
Sure, why not? Your wish is my command.
I was very confused.
What, so memorization wasn't working?
Oh, no, I didn't try to memorize it. I was trying to derive it. But it's,
Oh, yeah.
Here, that's technically like -3,000 pi would be equal to pi, right? When you make it positive.
Maybe. I have to think about it. Let's see
Well,
here.
technically I got to 0, but then I was like, I can't really do anything when it's 0. So then I turned it into 2 pi.
Okay. So this is the same thing as -3 times 2 times 5. Right? So actually we can represent it as a multiple of 2. Okay. And so yeah, this is really 2 times -1,500.
That's
So-
what I got.
Yeah, it's a
But that equals
pi.
0.
Right?
Yeah. But when you do that, wouldn't that technically be 0?
Well, then you'd have to add a bunch of 2 pi's to it.
Yeah. Well, I mean, I added just one more 2 pi to give me at least a value for that, because otherwise it would just say add 0, and I can't really work with that.
Yeah, you can add like 2 times, let's say, 1,005. 1,000. What am I doing here? It should say 3. Oh, yes. Yeah, okay, that's right. Okay, so when you add this much to it, yeah, it just becomes 0.
Yeah, so then I added one more 2 pi so that I could have a value because otherwise I can't really do anything.
You can evaluate the cosecant of 0.
We can?
Yeah, cosecant of 0 is the same thing as 1 over sine of 0.
And that's 0. Right?
You can evaluate it though. But yeah,
Okay.
that's undefined.
Yeah. Okay. I mean, I got that much. It's the second one, but I think everybody had trouble.
Oh yeah, this one?
I still don't. I'm not quite like I know how to do it when I look at my notes because I will
Yeah.
write down my notes really well, but
Radians per second is a theta over t. You want to get it in a distance over t. So you want to use this thing right here.
what is this?
Yeah, that's a good question. I probably should have given you the radius of his leg for you to be able to fully do the problem. So don't worry about it. I'm gonna give a lot of people a lot of
Okay.
I'll just chalk that problem up and give everybody points.
Okay.
Does that make sense?
Yeah.
If I mess up, then everybody wins.
Okay. I was trying to figure out. I mean,
I needed to give you the radius of his leg because then you can calculate.
what S is.
S is.
Gotcha.
I should have given you how long this dude's leg is.
All right. Now I feel so bad.
Nah, it's not like that.
Have a good one.
Mhm.